And one way to tame large numbers is by using logarithms, right? Because what logarithms tell us is that, it's the exponent, that the order of magnitude of the number that matters, not the number itself. And in statistical mechanics, you know that if you're dealing with 10 to the power 23 particles, you can throw in a few hundred particles or take a few hundred out, and it's going to have no effect, right? So the idea behind entropy, so Boltzmann introduced the idea of entropy, and the way he defined entropy for a system with energy E was, well, there's a constant KB times the log of omega of E. Okay, so this is a natural log. So this is log, E-based log. Okay, so this is the definition of entropy by Boltzmann. And the Boltzmann constant, which is an empirical constant, is roughly 1381 into 10 to the power minus 23 joule per Kelvin. Okay, so this is the Boltzmann constant. So in cosmology, often Boltzmann's constant is set to 1. So in cosmology, Boltzmann constant is set to 1. If it's set to 1, then temperature and energy, they will have the same units. And entropy, temperature and energy. And entropy will be dimensionless, right? All right. So the nice thing about this definition is that, suppose we have two systems, and one system has energy E, and it has some, omega 1 is the number of microscopic configurations, and another system has energy E2, and omega 2 is the number of microstates. Then if I combine the two systems together, then the energy, then the number of microstate is going to be this, right? If I consider, but the entropy of the combined system is additive. Right, so this is the nice thing about this definition of entropy. Because of the log, sorry, entropy becomes a, it becomes an additive quantity. The other thing is that this definition of entropy, because of the log, somewhat tames large numbers. So the large numbers are somewhat tamed because of the log.
I read somewhere,
so
because
what I'll do next is, sorry,
these things are grows with volume. These things are additive, because extensive things are like additive. Intensive things are not quite so.
Exactly. Yeah. That's another way of doing it. That because it's extensive. Yeah. All right. So, any more questions or comments? So what I'll do here is that we'll try to derive using the fundamental principle of statistical mechanics and the microcanonical ensemble, we are going to derive the second law of thermodynamics, okay? So we're going to, so let's take two systems and bring them together. And so the total energy of the system is E. So E is the total energy. And now when we bring, so, this is something that David Tong does very carefully, and I'm not going to spend too much on it, but the idea is that when you bring two, systems together, they're the, because the allowed energy levels, if they're quantum mechanical systems, they will change because there will be interaction terms in their Hamiltonian. So what we are assuming here is that, yes, they will change, but they will not change very, very drastically, okay? So if we assume that, then, we can apply the principle of statistical mechanics to the combined system. And this will be the probability of, a given microstate. So how do we compute omega of E? So omega of E is going to be given by, say, omega 1 of, so this is omega E total, right? So this is omega 1 E1 and omega 2, say, E total minus E1. And then we will have to sum over all the possible values of E. Okay, so this is going to be the so now if I use the, does this make sense, by the way?
I didn't get that quietly.
Right. So if you have, say, two different systems, one has some, some kind of, if one has omega 1 is the number of microstates, and the other one has omega 2, and you bring them together. When you bring them together, their total energy remains the same, right? But then what will happen is that, these two systems will interact with each other, and that total energy can get redistributed in many different ways amongst the two systems, right? So therefore, the total number of possible configuration will be a sum. Because if I look here, what happened here is that we took two systems, they were isolated, and we just considered them together. We didn't have to bring them together. It's just that for every configuration here, we have this many configurations. So the total number of configuration is the multiplication. But if you bring them together and they're interacting with each other, then they're going to exchange energy, right? They're going to exchange energy, and there should be a sum of energy. All of these different possibilities, according to the microcanonical ensemble, is equally likely, or they have to be considered, right? Because each of these configurations have the same energy, right? So we have to do a sum.
Yes, sir. The omega of E is this the microstate equation
For system 1.
Oh, so do these microstates depend on the distinguishability of the particles?
Yeah, they may or may not. I mean, that we haven't committed ourselves to. This is a much more general discussion.
So do each of the terms in this sum correspond to one partitioning of the energy?
What do you mean one partitioning?
like there's an E total, and then some of it has to be in one of the systems, and the other part has to be in the other system. So each term is one of the different ways we can divide the energies in, as long as
Yes,
its total is E total.
Yeah, exactly. There might be a better notation for this. And let me see if David actually does. I think he uses a slightly different notation for the sum, but that's it. Is there any confusion about the sum or no? Oh, what David does is that he uses I here. He uses EI, I, and this is EI, which is like, yeah, same thing. Yeah, I think that's better because then EI can take the value of E0, E1, E2, E3, blah, blah. Okay. Okay, so this sum makes sense, right?
Yes, sir.
Okay, so now we can use the idea of we can replace it with entropy. And hang on, sorry, let me just. Yeah, so we can introduce the idea of entropy, and then this becomes a sum of exponential factors okay, right. So one thing that we can do is that, all of these guys in this sum, they are all positive numbers, right? This is also a positive number. So from there, we can say that if you start, so this thing is greater than, say, greater or equal to each of these terms. Okay, so if I do this, then if I take the logarithm of that relationship, then I get the identity that S total is greater or equal to S1 of E1 plus S2 of E2. By E2, I mean, it's going to be E total minus E1. Okay, so I think I'm kind of out of time, so I don't think I can. Actually, I think I can derive the second law in 5 more minutes. Okay, all right, let me push through, okay? So let's keep this in mind. So does this make sense? Well, how this comes about? I'm just taking, yeah.
Sir, where does the greater than or equal to come from?
So yeah, I'm just taking the fact that, there's a sum here, but if I take one term here, that term will be either equal to this or less than this. And then I take the the logarithm of both sides. Okay.
So does this mean
here,
if we consider the two systems together, the entropy would be the same or it might increase?
Well, so far, it's just an identity. I'm not saying something physical because I don't know what the real energy of the system is yet.
Oh, okay.
Well, that's not true. I know the real total energy of the system, but I don't know what the real energy of each individual system is. Okay.
Okay.
Okay. So the idea is that now, if our system consists of n particles, so our system consists of, say, n particles, then the entropy is proportional to n, right? This is what Abhijit is saying. It's an extensive quantity, right? And so this is a large number. And what we see is that if I look at the expression for this guy, we see that we have exponentials of very large numbers. So so the sum, this sum will be dominated by a value of E, which, sorry, or E1 or EI, for which this thing is maximized, because we are looking at very large numbers and we are raising them to exponential. So the largest of those exponentials, the argument will be dominating that. So if you can find what the the value of EI that maximizes this thing, that will dominate this exponential. And let's call that number E star. Then what we have is this, if you look at this thing, this thing is, but E1 is E1 plus E2 is, say, E fixed. So we can replace derivative of E2 by derivative of minus E1. And then basically what we are saying is that we want to look at the solution to this equation when this thing is 0. So we want the value of E, we are setting the value of E to E star that maximizes this. Well, in this case, extremizes this. So if E star is that value, then of all these sums, I can say that the term dominating is the term which maximizes that thing above. Sorry, this should be E total minus E star, right? And we saw that this was greater than the original, something like this, right? So what we're saying is that if we have two systems whose entropy is S1 and S2, whose energies are E1 and E2, and if you bring them together, then we have some sort of equilibrium in which the energy of the systems are given by E star and E total minus E star. But then the total entropy of the resulting system as a result of bringing them together is either greater or equal to what the entropy was before. So this is a kind of formal derivation of the second law. Okay. So I think I'm out of time here, but let me if you have no, like, you don't have to stay around, but if you have questions, you can ask me.
I don't think I still got the greater than or equal to bit.
Oh, here, the first greater than or equal to?
Yeah.
Okay, let me show you. Yeah. So what I'm saying is that, each of these guys, this is a positive number because it's just counting. This is a positive number, right? So this whole thing is a positive number. This is a positive number. So you're summing positive numbers to get another positive number. So if you take only one term of this sum, that term is going to be either equal to the left-hand side or less than left-hand side. It's equal if there's only one term in the sum, right?
Why would it be less than?
So these are all positive numbers because they're all positive. So this is like 1, 2, 3, 56. And here is the sum, right? So if I just take one of these guys, it's going to be less than this thing, right?
Oh, I see. Each term individually. Yeah.
Yeah. Okay. And it's only when all of these are zeros, that's when they're equal. And then what I'm doing is that I'm taking the logarithm of that, and log being a nice like a monotonic function, it preserves that, and it turns it into a sum on the right-hand side. So taking the logarithm of this gives you this, okay?
Yeah, I got it now.
Okay, so any more questions? All right, so if not, have a good weekend, and we shall see you in the tutorial on Saturday. And I posted, oh yeah, I wanted to have a little chat about the assignment, okay? So I posted an assignment, and it's a little hard, and I will have some sessions where you talk to a TA or somebody to get help. Now, what I don't want is any form of copying or cheating. I am very, 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 very serious about this, okay? I have always found evidence of copying and cheating since I came to BRAC. Always. Every semester, every course, somebody does it. A lot of times I just let it slide, but I'm not going to do that anymore. So what I want you to do is to actually be, talk to each other, try to understand things from each other, but when it comes to solving and writing it up, you have to do it by yourself. Okay, do you understand?
Yes, sir. Yes, sir.
And the more words you use in your assignment to explain what you're thinking, the better it is. I will arrange for help in case you need help with the assignment, okay? And you can talk to each other, but do not copy. Take it? Okay. So I think that's it. If you have any more questions, we don't have anything more, let's end the class here, okay?
Okay, thank you, sir. Goodbye.
Okay, thank you.
Goodbye, sir.
Bye.
Assalamu alaikum.
Walaikum salam.